Hello, everybody. Today we have Chung, who will be talking to us about topological learning and its application to multimodal brain network integration.
Okay. I'll start the talk. This is about the brain network modeling, and so this is just based on this paper we just published last month. So it's a paper written basically with the student, and BJ is a postdoc that he will most likely working on continuously on this problem. He is basically working on one cycle. His research is mainly focused on one cycle particularly. We are now able to extract every cycle, one cycle, as a factorized representation, and we are trying to analyze across different groups. So let me briefly explain about the data we're gonna analyze. It's coming from the Wisconsin brain imaging laboratory. So if you go inside a scanner, something like this, then you will. This is a big magnet. It's a 3 Tesla magnet. So you're gonna basically scan this example at the single time point. So and multiple times you're gonna have this kind of time series data, so this is an example of the resting state fMRI when a person is doing nothing, and we have a 1200 time point, but I'm gonna show it at every 30 seconds. Now, if you do it, you may not see much differences. Actually, it's fairly stable. Now, if you compare this with our previous fluctuation of the fMRI timesheet, you can see a lot of fluctuation. While if you look at spatially, you don't see this kind of fluctuation much actually. So that's one thing to keep in mind in analyzing the network. It's not necessarily that noisy actually. Spatially, it's kind of stable as well. So how big the network data is actually, if you do the 3mm resolution, it's about 25,000 voxels. That's meaningful inside the brain. So number of connection will be, it's basically we have to divide by 2 actually. It's like 6 billion connections. How big the data is? It's about 5 gigabytes RAM memory, and that's what you're seeing. This is 55,000 by 55,000 correlation matrix basically. Now, if we increase the resolution, so you can actually get this kind of visualization out of the this data. Now, if you increase the resolution to 1 millimeter, we will have about 300,000 voxels. Now, that's 90 billion connections. And how big the data is? It's really big. It's 700 gigabytes RAM memory. Frankly, I was not able to model at this resolution. It's my goal. It's my goal, but it's too much computation. Seriously, some of you need to develop a really scalable topological computation tool. A lot of the computation tool is not best, for this data. I'm serious here. I try to use Elipser. It will go forever. I have to learn it like a year, possibly. I don't know. So I don't think we need a more scalable computation tool. That's so our approach, my group's approach is always about the speed and scalability rather than accuracy. Because if you stay with the Lisp filtration, you basically not going to go anywhere. You're just stuck at the possibly somewhere very small scale. So this is an example of the correlation network with the 300,000 time series, but I actually kind of cheated here. It's not a 300,000 time series here. What you're seeing here is about it's about 50,000 node actually here, and So even that, to display this network, I have to use the GPU. Otherwise, it's too much computation. And in the 3000 the node network, there will be about this number of one cycle or loop. And that's too many. We are actually interested in analyzing this number of loops. And because the zero-dimensional features, number of connected components, that's easy to compute, easy to quantify. But question is how you analyze one cycle. And so I think that's quite important issue. So what we actually did was it's too much computation at this moment. So we actually average the time series into 116 brain region, 1 brain region, 2 brain region, etc., up to all the way to the 116 by parcellating brain into this form. Then average it network. So what you're seeing is the example in this particular region at the small time point. So this is what we do. Then we're gonna correlate this time series and this time series, and we simply use a Pearson correlation. I mean, you can try some other more fancy way of measuring the dependency, like some sort of entropy-based, entropy or mutual information-based approaches, but correlation is good enough actually for our purpose, and that's actually baseline methodology. And so this is example. And so in this case, we have about 300 time point, and you're seeing a correlation matrix. And this is changing correlation matrix. So it's what we call dynamic correlation matrix or dynamic connectivity. And this example at the first time point, second time point, something like this. So you keep changing. This correlation matrix will keep changing, and we need to analyze it. Now, why this is important is changing correlation matrix. Correlation matrix is what? It's it belongs to space of partially definite symmetric matrix. Okay? So that's basically a manifold structure. Okay? So it's basically a curved space. So you can think about the correlation as a single point on this curved manifold. You can analyze this correlation, or even compute the distance. Now, the correlation, you want to model this as a partial definite. You don't want to model it as a non-negative definite. The reason is that if you model this as a non-negative definite, the couple of columns or couple of nodes will be dependent from the start, from the very start. So that doesn't seem to be reasonable. So, so you may also, that's why you want to model the correlation as a partial definite, so that there will be no artificial algebraic dependency to start with. And so, and those manifold structures. So that's, this is good mathematical object to play with, actually, I think. And so this is what we get. So subject level brain connectivity matrix. So we have about the bonded subject, and that's what we use. And so this is subject index. So I can represent my data in a single gigantic matrix. So this is subject index, and this edge index. So since this is 116 node, there will be total number of edges. That's about 65,000, 60 something around this number of the edges. So that's indexing for correlation. So that's my data. We analyze it. Now in this data we have
a quick question from the chat. So one question is, how can you compute a correlation at a single time point? So the correlation.
Oh, we are not computing a single time point. We are actually, so it's because it's too much data. I mean, you can do it. So if you do, so usually we use what we call sliding window. So each sliding window, you compute it, the correlation. And now, if you, but then this gigantic matrix data we are seeing will be dynamically changing. That's one direction we can push toward it, but that's hard. Dynamic correlation is not necessarily easy object to analyze, since there's nothing, not many people, I mean, the people, statistical people look at it, but topological, there are not much tools for what we call the dynamic TDA yet. So we want to analyze it in in a set. We basically collapse the whole time point. So we compute the correlation over the whole time point and collapse into single correlation. That's actually a good question. So next, so we are actually trying to move toward the dynamic correlation. So I would say that's, but I mean, we need to build some tools for the static correlation matrix first, then we can move to the dynamic version. So that's where we go. So we're going to introduce what we call the graphitization. This is I'm having difficult to. Yeah. So this is a paper we introduced this concept of graphitization. It's not just any kind of filtration. We do the filtration in a very peculiar way. So this we introduced in the 2011, I think. When I was at South Korea, and so this paper introduced that concept. And then we also did what we call the topological clustering. At that time, we used the GH distance. And so this is what we did it. And the GH distance clustering accuracy is almost 100%, while the Bartlett distance is only 50%. And all other, this is basically the existing graph theory features. So that's the main idea. Now, I'm going to contrast the Lip's filtration to the graph filtration. Lip's filtration, that I'm sure everybody knows it. So basically, we connected all the node if it's within the absolute radius, and basically construct this kind of the simplexes. Now, on the other hand, in a graph filtration, we don't do that. It's only constrained in the one skeleton. We are building a filtration on a graph, which is basically one skeleton. So we are not actually building a triangle or well, any base. There's no base. It's just the node and edges. So eventually we end up like this. So the reason that we do, and in a Lip's filtration, we increases the sizes, but in a graph filtration, we decrease it. The reason is that this is more natural for the brain imaging people. They usually threshold the edges to make the network sparse. So that's more like a convention. So then you get this kind of the filtration. Now, if you look at the Gaussian diagram of the Lip's filtration, you basically have this kind of the set, 0 dimension and 1 dimension. Now, this is a 2-dimensional scatter point, while this is a 1-dimensional scatter point. And I bet that might be the reason why the Gaussian diagram of Lip's filtration is hard to analyze, because you have a scatter point basically. So the question is how to make this into 1-dimensional projection somehow. So our idea is to make a filtration in such a way that we make something like this and something like this, 1-dimensional. And then the analysis of the Gaussian diagram will be fairly straightforward. So that's the idea. Based on those, we built this construct. So basically, graphitization is like this. We have a edge where we start with the complete graph. That's the usual setting. In this way, we always start with complex graph, and we're going to delete one edge at a time and make a binary graph like this. As we increase the filtration values. Basically, you only delete one edge at a time sequentially. Now, there are a lot of filtration in the graph data structure now, but why you want to only delete one edge at a time? because that makes this whole construct essential triviality, and you can analyze it mathematically quite easy without any tools. Okay? So it's very straightforward to analyze this construct. So you can even build the property model on this kind of the filtration structure quite easily. So that's what we did. I mean, these are kind of simple, very simple, trivial things. And so you machine this kind of the data representation out of brain. So we have this kind of brain network, and you delete the. I actually, by the way, the Lee, she was a former postdoc. She actually defined the graph filtration in a opposite direction following the Lips filtration. So she actually increased the sizes, but I changed it to decrease it to be more consistent with the biology people. So as you can see that the Betty numbers, Betty 0 decreases. Okay? That's known. But what about the Betty 1? Well, so we basically use the Kruskal algorithm, and it's a minimum spanning tree. Now this is critical. We're going to recycle this approach, and we're going to use a maximum spanning tree later. So this is what the persistence is in the case of the graph filtration. So let's look at this component. See when it is born and when it dies. So birth value would be here, and once it's born, it will not die. So it's infinity. So you can ignore the infinity. So all the connected component will have a birth value, but all the death value will be infinity. So you don't need to worry about the infinity, the death value. So it only have birth values. So forget about the death value. Okay? So I can write my Poisson diagram for the connected component just like this. Then what about the Poisson diagram for the cycle? Okay? It's one cycle here. So let's look at the birth and death values of this cycle. So cycle, we are talking about the complete graph. So cycle will be born. There's always cycle in a complete graph. So the birth value of the cycle will be minus infinity. So again, you don't need to worry about the birth value. And you only need to worry about the death value. So my Poisson diagram for the one cycle is just a one-dimensional scalar point. That's the nice thing about this simple filtration structure on a graph. I'm not sure any other filtration has this kind of simplicity, but one thing you may say that since this graph, we only have a 1D and 0D features. What about high dimensional features? Well, we don't worry about it. You simply don't worry about it. So this is what the BJ did. So he basically able to trace what happened to all this cycle in the brain network. Okay? And so that's what we want to analyze. Then you may say, oh, this is too trivial. And what you can possibly do with this trivial construct? Well, we can do a lot of things. So I'm going to explain about this birth and death decomposition of the edge set. If you understand this part, that's the biggest message I can give it to you in this talk. So you can actually decompose edge set into two partitions, two sets, in such a way that it will be destroying a cycle or creating a component. Now, these two events cannot happen at the same time when you delete the edges. When you delete the edge, it will either destroy a cycle or create a component, but it will not happen at the same time. So it actually forms a partition. So I can partition edge set, this whole edge set, into this part and this part, where this is a zero-dimensional homology, it's one-dimensional homology. Now, what if you combine this? So I call this birth set. T-H, birth set. And this birth set is basically a maximum spanning tree. So anything that's not a maximum spanning tree will be that set here. That's very nice, right? So, so whatever you do, whatever the graph operation you do, if you do the operation on maximum spanning tree, edges on maximum spanning tree, that operation that doesn't belong to the maximum spanning tree. You are doing it the operation on one-dimensional homology. Okay? So it's basically partition your operation, graph operation into two. It's quite nice. Okay? So if you do that, so this is just example. By the way, that the Betty 0, Betty 1 is always monotone because of this. It doesn't happen at the same time, so you can actually show that the Betty 1 actually decreases monotonically, while this one increases. So then we're going to compute the Wasserstein distance of the graph filtration. This is quite cool. So we have a random variable. Okay? Then the Wasserstein distance, H2 Wasserstein distance is defined this way, where the infimum is taken over all possible joint distribution. Then if you apply this to the Partition diagram, this is what you usually get it in the Partition homology literature, where this is the bijection. You need to basically identify the bijection from P1 to P2 on the scale of point. This is usually solved by the Hungarian. It's basically a kind of approach that requires a cubic runtime. I'm sure that there are slightly better method, but it's mostly more or less a cubic algorithm. So then but in our case, our Partition diagram is one dimension. It's one dimension. Okay? So this computation can be done quite easily. So what's the bijection here? Well, that's quite straightforward. We can actually solve this bijection problem analytically. The proof, actually, in the paper, proof we did was based on the, I think, inductive argument. I'm sure there are other methods for doing it, but so that's, I think this is a known result in the literature. So this is a zero-dimensional Wasserstein distance, and this is a birth value, and it's a bijection. But this bijection is basically, in the one-dimensional case, you only need to match ith smallest birth value to the ith smallest birth value. Okay? And it's amazingly cool. I mean, it's just so simple, so straightforward. In the zero dimension, one dimension, you just need to match the ith that value to the ith that value. That's all you need to do. In statistics, this is what we call the order statistic. And there are tons of the tools on the order statistic. There are a lot of tools out there. So it is possible you can combine this order statistics operation with the graph operation with the Partition homology, all combined together in this very simple concept called graph filtration. And I think you can get out of a lot of the mileage out of this.
And Mu, it's correct to say that the Wasserstein distance is so much faster to compute because you're really just working on the real line.
Yes, yes. So this is the idea. Our Wasserstein distance is so fast. It's basically one dimension. So there's no computational overhead. So if you want to apply this to the beam learning, you need a loss function there. You can use it immediately without much overhead. And that's the way. That's how we do the permutation test in our setting with 500,000 permutation. And we can do 500,000 permutation exactly like this, like a few seconds. And so so let me introduce this topological laws. So we're going to combine it. Now, why you want to combine this 1 dimension, 0 dimension? Because this one deals with the maximum spanning tree, and this is a non-maximum spanning tree. So it covers all the edge set. So I can construct this way. So this with the maximum spanning tree edges. This is non-maximum spanning tree edges. So there's no overlap. I can construct that way and still minimize it. So that's how we do it. And so that's how we do it. And so that's nice. Then where we use it? Where now I can do following using this, because this one, this minimizing this whole thing is a separate event. You can do the minimization in the maximum spanning trees and non-maximum spanning separately. So with that idea, I can do the graph matching. So I'm going to match this graph to this graph. This is 4 node, and this is 5 node network. Now this is a very hard problem in computer science. Graph matching algorithm, still people are still developing it. It's not trivial. Now we can do it very trivially. So we do graphitization this way. We do another graphitization. Now you're gonna do the both that decomposition. So this is MST. Then we're gonna match separately. MST edges match separately. Non-MST edges you match separately. So we're gonna match longer persistent the edges first. That's you should do it. Longer signal you should match it first, and smaller signal later. So that's what I do. Then there will be edges that's remaining. You just match it this way, and same thing. Longer persistence, you do it first, and sequentially you match it. I mean, this paper is under review, but I felt that the review didn't like. I thought this is one of the best approach to do the graph matching, but reviewer don't seem to like this approach. So anyway, we are trying to do something there anyway. So then with this matching, since we can match the graphs, then we can define the average operation or addition operation. Now we can add 2 graphs together because we know how to match them. So we're gonna add them and divide it by 5. And this is this. We can do that. And same thing with this. Now, I know there are something called the Wasserstein barycenter. I think the construct is slightly different. It's more or less same idea, but the construct might be slightly different because we are, anyway. So this is how we do. And so that's one. And we actually compare the runtime for the. So this is the logarithmic scale. In the logarithmic scale, this is our runtime, and this is the runtime of all other graphic matching algorithm. And this is spectral matching. Basically means that you match the eigenvalues of the matrix actually. Now our method is essentially flat. It's really flat, because there's nothing to compare. All you have to do is sort the edges. I'm just serious. How can you possibly that simple? I mean, it's a. So I like this approach. It's very, very clean, very short. The underlying algorithm is only like 5 lines. In MATLAB, it's only like 5 lines or 10 lines of code. There's nothing fancy. But I show the performance. Performance is just amazing. It can beat most of the graph matching algorithm. That takes forever to compute it. This simple approach can beat a lot of advanced methods without much. Why? Our approach is exactly matching topology, Gaussian diagram. We are actually matching a Gaussian diagram, while all other existing graph matching algorithms are not using topology. They are doing a brute force approach on a Euclidean space, basically, without looking at the actual topology. I think that why our approach, our simple approach can beat the existing method. Now, if you build something more complex on top of this, most likely you can beat any method out there. I think so. I mean, so we modified this Ernst-Laney model, which you know. So we basically put the connection property within a module and between module in this way. So here, this is 2 modules and 3 modules. Obviously, if you simply look at it, I would say anybody would agree that the topological structure of these 2 graphs are quite different. So we take that as a ground truth and see whether our method can actually detect this kind of the topology differences. Okay, so we generate 10 random graphs, looks like this. 10 out of 10 random graph looks like this. And we actually use the ratio statistics out of the between group distance. And this is 0D and 1D all combined. And it's within group distance. And we construct the ratio. So if this is small, then the group difference is small. So there's almost no differences. So we can actually use this statistic to see whether it's meaningful or not, or the statistically significant or not. That's what we did. Now this is an empirical distribution. Basically, we have to generate this statistic on the null, and to speed up the computation, we didn't actually use the full permutation, because if you do full permutation, this is the distance matrix. Okay? What you're seeing is Wasserstein distance between the one graph. There are 5 graphs in each group. Each of this is distance between the network. So if you permit half of the group labels in group 1 to half of group label in group 2, you essentially have to play with all the entries in this distance matrix. That's a lot of computation. So what we did is we developed what we call online computational procedure for the permutation test. We basically, instead of permitting half and half, we only permit 1 entry at a time. Basically, it's a mixing, very slow mixing. I mean, permutation is like a diffusion in a space of the permutation group. So instead of doing it, we basically do it's what we call transposition. So we did transposition, moving 1 label, and then what you have to do is you only need to worry about this row and this column. So we are reducing the run time to the linear time here. So that's how we do it, how we figure it out, and that will actually speed up the computation dramatically. And this is the performance here. So you can see it's a p-value, in this case, p-value. I mean, so we are comparing network with 2 modules and 3 modules. It's almost 0-0. While if you look at it, all other methods, it doesn't perform well. I mean, that's obvious because spectral matching, it's basically looking at the spectrum. So it's a geometric method. So it's not going to match 2 graphs quite reasonably well. So that's why. Our method exactly match the topology, 0-dimensional topology to the one-dimensional topology. So because of this explicit looking at the topology, we can actually perform better, I guess.
So the plus or minus value, that's sort of a error bar. But what's the first value? The first value.
Oh, that's a p-value. It's p-value. So p-value means that the smaller p-value means that we are basically rejecting a null, the equivalence. So smaller p-value means that the test is doing better.
Right.
So that's the indication. I mean,
you reject the null hypothesis that they're from the same distribution. You identify that. Okay, gotcha.
So that's how we do it, and it's quite good result actually. It's quite reasonable. I look at it, it takes a long time to learn this, while our method is just like a quick, very quick. So performance-wise, our method wins. Simplicity-wise, wins. Competition-wise, it wins. So I think it's a good approach. Then we do the subscript level learning. Then so we basically have a collection of the network. We are basically matching one kth subject, and we have some sort of the structural template. And we're gonna do some sort of regression, trying to move this network to somewhere and estimate it somewhere along the line. So we basically minimize this cost function, well, this is Frobenius norm. This is geometric term, because we still need geometry to constrain the network so that the front of the brain doesn't match the back of the brain. It is possible. So I mean, geometry is needed. This basically modular amount of the topology we are introducing it. And then we are estimating the actual network this way. So that's what we call the subscript level learning. But to do this, to minimize this, you need the gradient descent, but we don't do the numerical gradient descent. Our gradient descent is sorting based because you have to sort it. So you basically match the sorted both and that value, and that's basically get you the topological gradient. It's kind of ridiculous actually, if you think about this. So this is the usual loss function you set, and it's basically showing that just to show that there's the global minimum. It's around 1. So that's optimal the lambda value. That's 1 plus minus somewhere. I think it's not exactly 1, something like 2 or something. Plus, yeah, something like this. Then we can also do the group level learning like this. And so you combine it, and then you combine this part, and then you combine it, trying to learn. Group level, I actually we didn't like it. It doesn't perform well actually. It looks too similar. So I think approach would be we have to learn it individually. We have to learn this regression, topological regression individually. I think that's like a kind of topological smoothing, if you think about it. So this is a group level learning, and we didn't get much. So we apply this to the twin study. So data actually have twin. So what we did was that we actually computed correlation with an MG twin, identical twin. This non-identical twin. Now you have to swap the twin label. So it's actually permutation. This part is also permutation. So it's so we actually use the permutation or transposition in estimating this part. So we actually use the transposition test, estimating this part, doing all sort of like 500,000 permutation as well. And that's based on this, we actually get this result. So this is, I think this is the last slide. So this is you obtain heritability index if you're using original Pearson correlation. You're not going to detect much signal, but after this topological learning, we can actually detect far more signal. So I would say this approach can be used to align networks in a more topological way, then build more advanced statistical model on top of this aligned network. So you can think of this as an approach as more like a registration, topological registration of the network to network. In brain imaging, in order to do the statistical analysis, you actually need to align my brain or your brain into some sort of the common coordinate system. And our approach is exactly doing that at the network level using this Wasserstein system. So that's and what we want to do. We want to do this actually. So this is a kind of next project we want to do. So we want to build some sort of the complex topological structure out of the trees. We have this kind. It's a basically a collection of trees. that define the brain surfaces. So we can actually using some sort of I think this time I think we may use Morse filtration somehow, and we will try to come up with a scalable algorithm for doing this. We don't want to use a baseline Morse filtration; it's too computational heavy. We want to simplify this into really best scalable way. So that's end of my talk, and thank you for the here. So my office is actually located here.
Thank you so much. Okay, I would ask everybody before we have questions, if you could just unmute yourself and applaud the speaker. Okay, so are there any questions for Mu?
Oh, okay. Let me read some questions. The time. Oh, it's time series is the. It's time series of the brain activity. So it's amount of the blood oxygenation level. It's how much blood you are using inside your brain. That's what this time series actually measures, and this is especially at during the resting when you are doing nothing. Even you are doing nothing, your brain will use the blood actually oxygen. Actually. So that's what they and the functional fMRI rating. This generate the time series. Yes, it generated the time series at each point. Yes. And how you compute the code.
So we have a question from Dhananjay.
Hey, wonderful talk. Do you mind going back to the slide where you computed the ratio between the two Wasserstein distances?
Oh, yeah, sure. By the way, that's they are dependent. This is constant. If you sum LB and LW, that's actually constant. They are dependent. The reason so you could actually use one distance between group distance or within group distance, just like a K-means clustering. The reason we use this way is that it is kind of more stable in this way.
All right. If I understand this correctly, though, the first distance, the between group distance, you are computing the 0 and 1 cycle Wasserstein distance between graphs GI and GJ, where GI and GJ belong to the
two different groups actually. So C1 is one group, C2 is another group. So you can think of this as a clustering setting.
Right, and in the second one, they belong to the same group.
Yes.
So if you know which edges belong to the same group versus different group, isn't the problem already solved? Like if,
no, we are not doing a clustering here. No, we are not trying to identify the group label. Group label is already given.
Okay.
But based on, we are just seeing it's like this. I observe this network. I know it looks like there are two networks. They looks like topologically different. But how do you quantify that difference in terms of actual numbers? So I know, I know this belong to one group. I also know this belong to another group. So group label is fixed. I know group label, but still we don't know how close these are.
I see. Okay.
So this distance is, we are trying to compute the probabilistic distance. You can think of this as probabilistic distance. So you mix them all together randomly, then you're not going to observe. This is what we call null distribution. With respect to this null distribution, we want to see how far away this particular setting is from this null distribution. And then you count this, basically counting the area under this tail region. It's p-value. It's called p-value. Yeah. Okay.
I see. Thanks.
Any other questions?
Can I?
Sure, please.
I'm curious how these methods, obviously, it's a question that I would ask, how these methods, say, on the fMRI data match against the old correlation random field methods. Presumably, they're a lot quicker computationally.
Oh, it's very quicker. It's very quicker. I mean, one thing that the correlation random field assumes is that it assumes that you are matching exactly at the same position. So you have a correlation random field, then you are matching exactly the same two node
to
the two node. So that's the assumption. However, in our setting, we don't assume that. So I would say we can use this as a prior processing tool before we apply the correlation random field. It's more like a graph processing tool. I would view it as more like a topological processing tool to align one graph to the next, so that we can do the comparison.
Okay.
I think.
Okay.
Yeah.
I'll ask a question. So I asked a question about the p-values and the standard deviations with the plus or minus. The standard deviations you just compute from the sample.
Yes. So so it's like this in the validation table. I don't know where is my. So we actually did. So this is we randomly generate 5 networks, then get a p-value. However, this is whole thing is random. It's fluctuating. So even the p-value is a random variable. So because of this, you have to do the simulation 50 times. I think 50 times is good enough. It will, because if you look at the standard deviation, it's almost very small. Let me see, where is my?
Yeah.
So.
Yeah, it's quite small compared to
the
other methods.
Yeah, here. You see? Actually, in this particular case, standard deviation is quite large, but well, it's not doing well. Actually, this is but still it's doing well compared to other methodology. So.
Oh, definitely.
Are there any other questions for our speaker?
Oh, by the way, the MATLAB 2 is already uploaded in my webpage. So if you go to there, you can just download it and play with it. It will automatically compute the Wasserstein distance for the given to the edge weight and edge weight of the graph. It will compute the Wasserstein distance and give you the number. So you don't need to do anything.
Great. Okay, so I guess we'll take the rest of the questions online. So I'll end the recording here.